Today, we are exploring a cornerstone of statistics that many students find challenging, sampling distributions. We'll look at why this is a hurdle and how we can use mathematical reasoning to move students from simple calculation to conceptual understanding. We often confuse the distribution of individuals with the distribution of sample statistics. We must clarify the difference between the population distribution, the distribution of the sample, and the sampling distribution, the last of which is not just a set of data points, but rather a theoretical map of what happens when we sample repeatedly. Consider a list of 1,000 AP exam scores. To estimate the true mean, we collect random samples and calculate the average score from each sample. The center of these averages becomes the estimate of the true average of all 1,000 scores. When we work with much larger populations where it is impossible to know the true average, we can assume the samples are good enough to make, can we assume the samples are good enough to make an inference about the population? This concrete activity of data collection gives us a visual of sampling variability. Some samples will have many small values with a low average, while others will have large values with a large average. The unpredictable nature of sampling variability is easy to see when you can create a dot plot of these sample means. Lidke et al. State that student-centered classroom activities like this forces teachers to shift away from traditional lectures and supports diverse learners. We also struggle with sampling distributions because it requires moving from what is seen to what is abstract. We can encourage students to use mathematical reasoning by asking questions like, what would happen if we didn't stop at 30 samples? Mathematical reasoning is the glue that binds our classroom data collection to the unseen mathematical reality needed for inference procedures. American College of Education. The true sampling distribution is just created from 30 samples. Isn't just created from 30 samples. It's made up of all possible samples of that same size. If we could plot every single one, the distribution would become perfectly symmetric. If we account for every possible combination, then the center of those means must equal the true population mean. We trust this because of deductive reasoning, which uses proven logical steps to reach a valid conclusion. American College of Education. At last, we come to meaningful conclusions. Building the bridge from 30 to 300 to 3,000 samples, we see the randomness transform into something predictable. This helps students become competent thinkers by justifying how the pattern of 30 dots becomes the bell curve. So why do we care so much about a distribution we can't see? Because statistical claims influence real-world decisions. Whether evaluating AP score equity or medical trial validity, citizens need to identify sampling bias in real-world contexts and not just become passive consumers of data. This reasoning is essential for informed decision-making. When students understand the spread of a sampling distribution, they can determine if a headline or a claim is statistically significant or just a lucky outlier. Don't just memorize some formulas, understand the why. Every statistic you see is backed by infinite, invisible samples. If you understand the sampling distribution, you uncover the truth.